So we'll start by discussing galaxies. And we're going to do this with a little bit of historical perspective by starting with a question that a couple of hundred years ago we didn't know the answer to. And that is, are there galaxies other than the Milky Way? Are there galaxies outside of our own? This drawing here that you're looking at is a drawing of what was called a spiral nebula at the time. This was from a magazine in 1873. People observed that there were these spiral things in the sky, but they didn't know whether they were just clouds of gas or something like that in our own galaxy, or whether they were actually galaxies entirely outside of our own. The resolution to this problem came in the early 20th century. And it came partly through the work of this woman here, whose name was Henrietta Swan Leavitt. She worked at Harvard College Observatory in the early 20th century, doing very detailed and painstaking work, examining the photographic plates of observations of many, many, many stars. And she made a very important discovery. There was a particular type of star that she studied on these plates. And you're seeing an animation of this type of star here. This is something called a Cepheid variable star. And if you look at this animation, you'll see that it's pulsing. This star is getting bigger and smaller and bigger and smaller again. And as it gets bigger, it gets brighter. As it gets smaller, it gets fainter. And it does this regularly and periodically. What that means is that this star is something that we call a standard candle. In 1912, Henrietta Leavitt published a relationship showing that the period, the time at which these stars take to pulse, is directly proportional to their luminosity, how bright they really are. What that means is that if we can measure that pulsation period, we know how bright the star is. And then we just need to measure how bright it appears to be, and then we can get its distance. We call this a standard candle. You see a picture here of a candle of some fixed brightness. As it moves farther and farther away, it gets fainter. And if you know how bright it really is, you're able to measure the distance by figuring out how bright it appears to be. So, the next piece in this story brings us to Edwin Hubble, one of the most famous astronomers in the early 20th century. And Hubble did many things, but among them was observations of a Cepheid variable star in the Andromeda galaxy. This was one of those spiral nebulae, one of the largest and brightest ones. And Hubble found that there was one of these variable stars in Andromeda. He used this relationship discovered by Henrietta Leavitt to measure the distance to this galaxy, and therefore found that it was far, far too distant to be part of our Milky Way galaxy. The Andromeda galaxy is about 2 million light years away. It is much too far away to be part of the Milky Way, and that therefore there are galaxies outside of our own. So this was a fundamental expansion of our conception of the universe. It has been said that this particular star is the most important star in the history of cosmology. And it's for that reason. It told us that there are galaxies outside of our own. Now, of course, we know that there are lots and lots of galaxies. We have all sorts of exquisite pictures of them, like this one from the Hubble Space Telescope, showing a giant elliptical galaxy and a bunch of smaller galaxies as well. We have catalogs and surveys from hundreds of thousands of galaxies. What you're seeing here is a visualization of what it might look like if we could fly among the galaxies from one of the largest of these surveys, the Sloan Digital Sky Survey. This visualization is made from real images of the galaxies and their real positions in space. And what you should notice here, in addition to just how many galaxies there are, is their spatial distribution. Notice how they're clumped together. And if you look closely, you might see what look like linear filamentary structures connecting those clumps. You can see that a little bit in how we've paused the simulation here. So we're going to come back to that structure later. So remember that. For our purposes today, though, the most relevant galaxies are the spiral galaxies. And the reason for that is that they are rotating disks. We can use the rotation speeds of galaxies to determine their masses. Essentially, the more mass there is inside the orbit of a star or a cloud of gas, then the faster it will rotate. So here is an animation of two different rotating spiral galaxies. The differences here are maybe a little bit subtle, but once you know what to look for, you can see that the galaxy on the right is rotating faster than the one on the left, especially in the outer regions. There are a couple of little plots below each galaxy there, and those are showing the rotation speed plotted against the distance from the center for both of these little model galaxies. The plot on the left and the galaxy on the left shows what we expected to see when we first started making these kinds of observations. As you get out to the very outskirts of galaxies, the amount of stars and gas is decreasing sharply. And we therefore expected that the rotation speed would be decreasing as well. However, it turns out that this is not what happens. That galaxy on the right and that little plot below it, this is what we actually see when we look at real galaxies. So here is a bigger version of this little plot showing the rotational speed of the material in galaxies versus the distance from their centers. And that line that's labeled expected is what we would see if the only mass in galaxies were the stuff that we could see. Instead, we measure something more like this purple line at the top that rises and then flattens out and keeps being flat at fairly high values for as large as we can measure it. That is telling us that the outskirts of galaxies are moving much faster than can be accounted for by the mass that we can see. There must be a whole lot more mass in galaxies at large radii that is completely invisible, but that we can see via its gravitational effects. So this was one of the first signs of dark matter. The study of the rotation of galaxies and the implications for their masses was pioneered by this astronomer, Vera Rubin, in the 1970s and the 1980s. This is a picture showing her in the 1970s using some of the instruments that were used for astronomical measurements at the time. I honestly don't know exactly what this instrument does. This is not something that we use anymore. We'll hear more about Vera Rubin in a little bit towards the end of this talk. So when you think of a galaxy, what you should really think of is a picture a little more like this. That luminous matter that we can see, all the stars and the gas, is actually a tiny little bit that is surrounded by a much larger amount of mass that is invisible, something that we call a dark matter halo. The bright parts of galaxies are tiny specks in spherical halos of mysterious dark matter that extend to at least 50 times the size of the visible disk of the galaxy. We'll turn next to galaxy clusters. These are giant collections of galaxies that are bound together by gravity, and they are the most massive gravitationally bound objects in the universe. If you look at this image of a cluster closely, you'll see that in addition to the mostly yellowish galaxies that make up the cluster, there are a number of fainter bluish streaks and arcs. You can maybe see them a little bit better in this image of a different cluster. You can also see from this image that some of those blue streaks look like distorted pictures of galaxies. And in fact, that is exactly what they are. One of the consequences of general relativity is that mass causes space-time itself to curve. And this curvature causes the bending of light rays from distant objects. This is particularly apparent for very massive things like galaxy clusters. The masses of these clusters act like a lens, and that lens bends and focuses the light from the galaxies behind them in a process called gravitational lensing. So those blue streaks that you see are the distorted and magnified images of galaxies that are behind the cluster. Their light has been bent by the curvature of space-time due to the gravitational field of the cluster itself. We can make detailed models of this lensing process, and those models enable us to determine the masses of the galaxy clusters. And when we do that, what we find is that their masses are much, much larger than the combined masses of the individual galaxies and the gas that we see in the clusters. The vast majority of the mass in these clusters is invisible and apparent only by its gravitational effects. This is the same dark matter that makes up most of the mass of galaxies. We can tell by measuring the mass of clusters that it makes up most of the mass of clusters as well. Galaxy clusters are also important because the number of massive clusters is very sensitive to the total amount of matter in the universe. So by studying galaxy clusters, we learn not only that most of the matter is dark matter, but also how much matter there actually is. And we're going to come back to this point when we put all things together later.